Okay, so the question is, does reducing gradient time, what's the effect in terms of DDA or in DIA mode? So this is now a figure from a tutorial kind of paper that we wrote, was led by Tina Ludwig, a former postdoc in the lab, and essentially this is some data that says as you shorten the gradient length from 90 minutes down to 30 minutes and you run either in DDA mode or in DIA mode using either 32 SWATH windows or 64 SWATH windows, what happens as you compress the gradient? And what you can see here, I think what you can appreciate is that so I think the absolute numbers are not so critically important here, but what I think you can see is that the slope of this line for DDA is a little bit steeper than the ones for DIA in either 32 window mode or DIA in 64 window mode. And so this is the first observation that made us think, okay, it might be reasonable to start squeezing these gradients, that at the protein level it seems like we don't lose that much information going from 90 to 30 minutes. And you can ask why this would be, and I think there's kind of some intuitive reasons. So in DDA, you're asking the machine to acquire MS2 spectra on as many precursors as it can, and this takes time. And so as we squeeze the gradient, we're going to get precursor undersampling. In DIA, there might be some effects, of course, from squeezing the gradient as well, but this is probably primarily due to a loss of selectivity, so more things are overlapping in the chromatographic space because of a loss of a little bit loss of chromatographic resolving power and potentially some suppression effects. But these things also, of course, affect DDA. But I think you could imagine, or the intuition is that the primary loss in the DDA data is going to be due to this precursor undersampling, and this is, I think, the effect that we're seeing here. So this is the first kind of clue that it might be useful to run in DIA mode with short gradient analysis. The caveat here is, of course, and anybody who's kind of been in the targeted proteomics world knows that we need to be able to maintain duty cycles. So as if this is some peptide which is eluting, in order to reconstruct faithfully the area under this curve, we need to sample 8 or 10 peaks across this point. And if we're going to squeeze the gradient and make the peak width smaller, well then we've probably got to bring the cycle time down. And so I think probably most of you are very familiar with this, and in fact sometimes when I teach courses with Mike McCoss, he always cites this paper, there's sort of 50 years of chromatography experience telling us that we need to have good chromatographic sampling. So this is sort of a classic paper from Matthews and Haynes showing that, well, they sample all the way to 100 peaks, but basically as you get down below 8, 10, maybe 6 points, your accuracy and your precision sort of drops off the cliff. So this we need to keep in mind as a caveat. And so when we were thinking about getting set up with this Evosep system, we thought, well, maybe we'll try and do some tests to sort of simulate what a Evosep run might look like on an exigent ultra nano LC, which we use very frequently. So what we tried to do was to basically start with a kind of a standard method that we would use that would be so this would be a 90-minute gradient with a 20 centimeter column at 300 nanoliters per minute, and we would do the DIA analysis. This was at the time on a 5600 triple TOF, and then we would stepwise go in the direction of essentially what an Evosep method would look like. I should point out that you cannot you can sort of run an Evosep-like gradient on this system, but you cannot get the speed really of the Evosep. So the overhead time for one of these analyses is going to be 20 minutes instead of 3 minutes. So I'm not saying that you can do that kind of analysis with the system necessarily, but we could at least sort of simulate what we think the results might be when we were going to move to the Evosep system. So the first thing we did was shorten a little bit the column, because we know we're going to have to use a little bit shorter column with the Evosep, and then we went up with the flow rate from 300 to 1,000, basically one microliter per minute. Then we went with the gradient down from 90 minutes down to 20 minutes, and then we tried a whole bunch of a variation of different methods in the DIA acquisition method, either 64, 32, or 100 windows. And if we increase the window, then we've got to tune down the MS2, the accumulation time, so from 50 to 25 to 15 milliseconds. And we also did a little bit of fiddling with the MS2 mass range, which helps in some cases, and the loading. And the question is, as we sort of stepped away from this kind of more standard nano approach, going in the direction of a kind of an Evosep-like method, what's actually the effect of these things? And so we were running just a regular HEC293 lysate. in SWATH mode on this 5600, as I mentioned. Okay, so this is essentially an overview of what that data looks like. So you can see that as you reduce the column length, as you increase the flow rate, we lose some peptides, right? So this is expected. I don't think this is kind of news, but it's interesting to see at what rate we lose things. Actually, the flow rate increase is a bigger loss than other things. But essentially, when we look at what the results are, so we get a loss of peptides. We don't get so much loss of proteins, and if we look at the best method here, the most optimized SWATH method, this is now in this 20-minute gradient. At the protein level, we can get roughly sort of 80 or 90%, probably 90% of the proteins that we saw in the prior methods. So this we were kind of reasonably happy with, and we said, okay, let's try the real thing now in the Evosep. I also want to mention that, of course, while we were working on this, this first paper from Evosep came out, which was a collaboration between Evosep, Matthias Mann's lab, and I think Jesper Olsen's lab, and it also, I think that it didn't escape them that it might be a good idea to do DIA analysis in this short gradient. So this is a figure from their paper here, and you can see that this is using the sort of latest and greatest quadrupole Orbitrap platform. They can get really some impressive numbers. Again, using this sort of 20-minute gradient approach, they can get sort of 5,000 proteins. These are the CVs, and the difference between the red and the blue is basically the cycle time. So what I was talking about earlier, they have the so-called slow method and a fast method. I think it's likely that this slow method is a bit undersampling, and that's why they see a bit less good precision with this slow method. With this fast method, they have a little bit better precision because they're probably reconstructing these chromatographic peaks better. And in fact, I would say maybe even the fast method could be a little bit faster. We're normally running duty cycles of something like 1.4 seconds there. But nevertheless, I think this data is very impressive and really shows that DIA could be a good way to go with these short gradient methods. So the conclusion from this first part is DIA or SWATH type approach and short gradient analysis a good match? And I think the answer is, well, my answer is yes, at least. There's some expectations, I think, from theory and also some data indicating that DIA should work well with short gradient analysis. And I think we also saw this from Marcus this morning, Marcus Ralser this morning. We do think there are obvious reasons why DIA should be less affected by gradient shortening than DDA, but we have to keep in mind all these caveats about duty cycle and chromatographic sampling. We also have to sort of appreciate that there will be a loss of selectivity because the peak capacity of the separation is going to go down to some extent, so that might affect how we set up our DIA method. We want to try and buy back some selectivity by, for example, using more windows or so on, and we could also potentially have some suppression effects.